Welcome back everybody to environmental science. So here we do the section on electricity, starting with a question. If you've ever been electrocuted or like touched somebody and shocked them, right, and they're like mad at you and you didn't mean to, or touch an electric fence or been shocked elsewhere, okay, well, that's going to be our starting point for this. I did touch, it wasn't quite so obvious as this, it was like a control unit, but I touched an electric fence once and it wasn't fun. So, electrons. This is the culprit, not whoever shocked you. All right, they're tiny. They can move, but only through certain things, which are conductors, right? Everything has them, right? You have them, and so does everything else. They're everywhere, and lots of them. And they can have varying amounts of potential energy, right? So when you got shocked, what happened is that you created a pathway for electrons with a bunch of built-up energy to release it as they move. And they did. And they released it into you. Isn't that fun? Okay. Electricity flows in electric circuits is our starting point in this one. Electricity being the flow of electrons, right? From places where they've got high energy to places where they've got low energy. Just like how water moves from places where it has really high potential energy to places where it has really low potential energy, right? And when you have an electric circuit, right? So we've got these batteries, right? And we close the switch so that this is complete, right? Or flip the, light switch on, right? And then now electricity is flowing in this circuit. And the first thing we're going to do in this section is kind of break down the parts of this, right? So voltage, right? Because we don't want to be physicists about it necessarily. We're just going to think of this as being like push or pressure, right? So the battery is where the push comes from in the electrons. It's what gets them to that high energy state to where they want to go somewhere, they want to fall, right? It's like the equivalent of lifting a bunch of water high up in the air, right? Is what the battery essentially does. Provides the push for the whole thing. It is measured in volts. So if you've ever heard of something that's, a 9 volt, right? That's a measure of how much pressure or push is coming out of it. Power outlets are really high. Like 120 volts is really hot, right? Is the term for it whenever they're live and they have power, right? This is a lot. I mean, even every outlet that you see anywhere has a ton of energy in it, and it needs to, even though that can be very dangerous. And actually, outlets in other countries are sometimes twice as high. They're even higher than this amount, right? The next part is current, right? So, if somebody sticks something into an electric socket, right, then they're going to get a ton of electricity flowing out of it, right? This is sort of like what we talked about with rivers, right? Like discharge. So we've got the push coming from the battery, right? But how much electricity is flowing through it, right? You can think about this as being like the size of the stream or the size of the tube. That's the current. This one is measured in amps, and this is what actually can hurt people, right? Or even kill them whenever they get electrocuted. It's not the voltage, right, that ultimately harms a person, especially if there is this other thing that we'll talk about in a minute. It is the current, right? It only takes something like 1/10 of an amp running through your heart to stop it forever, right? Voltage is not really the problem, it's the current, the actual flow of electrons through there that is the issue, right? And, as you can kind of imagine, right, the more voltage you have, the more current, right? So if this battery, I don't know, all of a sudden ate a mushroom and became 10 times as big, it's going to push 10 times as hard and you're going to get 10 times more current. And you're probably going to blow this light bulb, right? Because you're putting way more electricity through it than it's actually meant for. The next thing, right, is power, right? So that combined measure, right, of voltage and current together makes power, right? Which is what we generally think of, right? Horsepower, right, is this ability to be able to do work over time, right? Now, what we don't want to think is that we're paying for power, right, when we use appliances. We're still paying for energy. We're paying for power over time, which is energy, right? So kilowatt hours is a measure of energy, right? Generally, appliances have totally different wattages depending on what it is, right? So like clothes dryers or like washer dryers, right? The reason why they sometimes have to have special outlets or be on their own circuits is because they use an absolute ton of power, right? On the other hand, well, this doesn't even have a computer on here. Oh, it does, yeah. So a computer actually doesn't use anywhere near as much power as things like a dryer, right, or other machinery. So common wattages for household stuff, anywhere from 50, right, to a few hundred, right, depending. And this kind of gives common figures for where a person's kilowatt hours per day might come from. Notice, right? So 15,000, right? This is 15 kilowatt hours per day times 30 days in a month is 450, right? And our typical energy bill might be somewhere in that range. I think mine's more like 90, but I have a small unit, so that works. Yeah, so we said that, okay, electric outlets just have voltage, right? But amps are the things that are dangerous, right? So why don't they just put the amps on the outlet, right, if that's the dangerous part? And the answer is that the amps, right, the amount of flow depends on the voltage and this other thing called the resistance, which slows things down. So notice our diagram here, right? So we've got the push from the voltage, right, and the current, which is a measure of the flow, but resistance, right, is another factor in here that slows everything down and makes the electricity flow through there more slowly, almost like taking the hose and doing this with it so that it's hard for the water to flow through, right? Or you can almost think of this as like weight that has to be carried. Actually, you know, common term for this would be load. You always want some of this, right? So notice, right, we have our battery, right? And things go from here where they're charged up through the light bulb, or it powers the light bulb along the way, loses some energy here, loses all of its energy all the way down to the negative end. Well, if you didn't have a light bulb here or some sort of resistance, then what you would have is this thing called a short circuit, right, which has no load. And essentially what's going to happen is that battery or outlet or whatever it is going to take the shortest path available to it and essentially dump, like a dam bursting, all of its electrons, right, at an incredible speed, just instantaneously, right? You know, if somebody does take a fork and stick it in there, right, the fork doesn't have any resistance the way that a light bulb does. So what that person has essentially done is they have completed the circuit from the really high energy outlet to themselves without adding resistance along the way, and you need that resistance along the way. And they're going to pull so much electric current out of the wall that it's probably going to explode, and it's going to be really bad for them as well, right? And it's going to trip this thing called a circuit breaker. So if you've ever seen one of these, right? And these things essentially are safety valves, right? So whenever you have too much electricity flowing through the circuit, right, it essentially gets so hot. Well, okay, this is the old version. They don't use these anymore. They use a new version. But essentially the old version was it would get so hot that it would essentially cause something to melt, which whenever it melts would automatically disconnect the circuit so that it couldn't go anymore and would prevent the person from just using ridiculous amounts of electricity, right, or causing an explosion or whatever else, right? So if you've ever wondered what the purpose is of these things, these are actually safety circuit breakers here. Triggering them is ultimately good compared to not triggering them. Okay, final thing, right? So we kind of skirted over this discussion a little bit when I talked about turbines and the transmission of electricity, right? Is you can essentially have two kinds of electricity, right? You have DC, like from a battery, versus AC, like from the outlet, right? If you've ever seen something that says, you know, 120 volt AC, stands for alternating current, right? Versus direct current, where it's just a steady push. So essentially, alternating current, right, goes from high voltage to low voltage and alternates at something like, I want to say 60 to even 120 times per second. And if you don't really understand why this works, I don't understand it either. And as far as I can tell, very few people actually really deeply understand why this can actually work to power stuff, and I'm just going to leave it at that. Alternating current is magic. That's where the miracle happens. But we don't necessarily need to understand the deep physical details to know that these two are different. They have different properties, right? So something like this goes from alternating current AC in an outlet, I keep pointing over here because that's where the nearest outlet is, to direct current to be able to power something else, right? Or you can have something called an inverter, which goes from DC to AC. That's all we're going to care about for those for now. Now, I mentioned that outlets are 120 volt AC. And now we can ask the question of why, right? Like, okay, we see that there's a difference and it's complicated, whatever, right? So like, what actually is the difference between them? So kind of a long story short version, way back when, you had Nikola Tesla and his AC, which nobody understands except for him, and you have Edison trying to promote DC, and there was this whole thing with this element that I'll put in a note. It was bad, right? AC is ultimately used at industrial scale and is kind of the norm for mass power distribution because you can use this thing called a transformer to be able to easily move around the voltage of something that is alternating current, or AC, right? So essentially it is much easier and much more energy efficient to travel things over long distances with a massive voltage, as high of a voltage as you can possibly get, right? So what happens, and there is no such thing as this, right? This thing is called a transformer, right? That steps down power. If you've seen those, green cubes or boxes or whatever, that's essentially what it's doing, is it's taking in really high voltage power from elsewhere that is being transmitted long distances and stepping it down to a voltage that you can use, right? We don't really care about the details here, right? But you have your generating station, right? It steps up the voltage to be as high as humanly possible, right? So notice this is in kV. That stands for kilovolts, which is like thousands of volts. So your outlet is 120. This one is 500,000, right? Super duper high voltage on these transmission lines for huge distances, right? And it doesn't get stepped down until the very end when it gets to you. And that is why it comes in as alternating current. And that's all we're going to learn about electricity. We're going to do renewable energy next.